Today we are going to discuss section 1 of the material, which introduces you to the field of statistics and talks about data collection. I always like to start with some examples. The nice thing about statistics is that whether you're in business or medicine or education or politics or sports, any field that you might be interested in involves the use of statistics at some level. So let's just talk about some examples. I'm going to use two specific examples so that we can start to think about the different types of statistics that we deal with in this class and in our everyday lives. The first example I'm going to use is the free throw percentage of Anthony Davis. So one of the main things to always think about whenever you read a statistic, like if you're looking at the sports page, what you'll notice is when you see someone's free throw percentage, there is no error involved in that statistics. And that's one of the things that I want you to pay attention to as we begin the material in the class. Is I want you to begin thinking about whether or not a statistic involves error, because what you'll find is that some statistics do and some statistics don't. And it's important we make that distinction between when a statistic does include error and when it does not. So let's think about Anthony Davis's free throw percentage. And if you think about it, there is no error involved in that statistic, but let's talk about why. Well, the reason why we have no error is when you look in the newspaper and you see his free throw percentage, basically it's going to represent over a certain period of time what percentage of shots he's made. And the thing that tells us there's no error is, for one, the newspaper's not going to report any error. But the big thing is that over that period of time, we know exactly how many shots he's taken and how many shots he's made. So when you have all the information, when you've collected data basically from your entire population, you have all the information, that means that there's no error involved because you're not trying to estimate. And that is one of the big distinctions between our branches of statistics. So when you think about something like Anthony Davis's free throw percentage, it is a descriptive statistic. You're just describing his performance over this period of time. Whenever we do descriptive statistics, there is no error, assuming that we measure things accurately, and we are going to make that assumption. This is a methods class, so we really focus on the statistical part of it. We're assuming that we measure things accurately, but assuming that everything is measured accurately, when you're simply describing the data set you have, there is no error in the statistical process, because in the statistical process, you have all your data and you're just summarizing it. Another example that we commonly see is something like the president's approval rating, where there is error involved. So there's a couple ways to know that there is error involved in the statistic. The first way is if you ever look in the newspaper or see it online, and you look at the president's approval rating, you'll notice that if it's done properly, and of course it typically is, then along with the approval rating, they will report what's called a margin of error. We also call that an error tolerance in statistics. That margin of error tells us that there must be error in the statistic. So just for an example, suppose the president's approval rating is 40%. It'll also report that margin of error of plus or minus 3%. So we get 40% plus or minus 3%. So where does that error come from? Well, it's just the opposite of free throw percentage, because in this case, notice we do not have all of the data. They did not ask every single person what they thought of the president's performance. Instead, what did they do? They took some smaller group, they asked that group their opinion on the president's performance, and they reported that. They report that as 40% or whatever that value is. And basically what they're doing is they're using that 40% to estimate what's actually going to happen for the entire population. So in that case, that 40% plus or minus 3% tells us that for the entire population, we are confident that the president's approval rating is basically between 37 and 43%. But there's error involved because we didn't collect data from everyone. So that error comes from basically this idea of probability. And we spend some time in this class talking about probability, a good bit of time, because whenever you do inferential statistics, this is an inferential statistics. Inferential statistics involves error. That's one of the big differences between descriptive and inferential statistics. Descriptive statistics do not include error. Inferential statistics do, because we're now estimating. But when you do inferential statistics and you estimate that population based on your sample, you don't have all of your information, which means we know we have error. What we do is we use this idea of probability in order to control and calculate that error. And we'll spend a lot of time throughout the course going through that process of how this probability works. The one other thing I do want to mention is I want to mention that I said if the president's approval rating is 40% plus or minus 3%, what that really tells us is that we're confident it's between 37 and 43%. I don't want you to think we're 100% confident of that, because that is also not the case. Usually when you see those kind of things, that's actually called a confidence interval. When you go from 37 to 43%, we're confident that it's within that interval. Typically those intervals are 95% confidence, so that really means we're 95% sure that the president's approval rating is between 37 and 43%. There's always a chance that it's just not right, and if you do a 95% confidence, that means there's a 5% chance that you're wrong. That 95% that you'll see when you do these kinds of inferential statistics, that is nothing more than a probability value, and it's a probability value based on the method that you use to collect your data, which is part of what we'll start to talk about today, is how we collect our data. So like I said before, the nice thing about a class like this is it's something that you see every day. You see statistics in any kind of professional world. You're going to work for a place that uses and looks at statistics in their decision-making process, at least part of that decision-making process. So it's a very important tool, and it's a very common tool used these days. Let's just talk a little bit about what we study in the field of statistics. It's really broken into four components. There are really four main components of our field. The four main components are how we collect data, how we organize that data, and then how we analyze and interpret that information. In this first section, we really focus on the idea of just kind of introducing what statistics is, and then we start to talk about that first component, which is the data collection process. The data collection process is a very important component, and it's one of the components that is often overlooked whenever people that aren't really familiar with statistics try to do statistical analysis. The way that you collect your data is key, because that probability that I mentioned before, if we don't collect our data in a proper way, then we're not able to calculate that probability. And that probability is key in order to be able to perform inferential statistics and make those inferential statistics accurate. So the way we collect our data is really, really important. I can tell you, I used to do some statistical consulting, and one of the biggest issues I always had was people would come to me, and they would want to do a certain type of analysis on their data, but they had already collected their data. And about half the time, what you would have to tell them is, we would have to tell them, well, we can't do that kind of analysis because you didn't collect your data properly. So the way you collect your data can really limit what you're able to do and not do in terms of analysis. Organization of data, we don't really do much of that. That's mainly done electronically these days. We have super sophisticated software, and it's really easy to organize and manipulate very large data sets these days. So the organization process is something that we don't really deal with much in this class. Most of the semester, of course, this is a methods class, so most of the semester is focused on those last two components. And to me, the interpretation is just as important as the analysis. If you can't tell me what that outcome means, then it's not very useful in the context of the situation. So those last two components is really what we spend a lot of the semester on, is once we do collect that data in the proper way, how do we analyze that data, and then ultimately how do we interpret that information, and how is that information useful to us. In order to go through some terms, some of the basic terms that we use, you should have already read these in the notes. If you haven't, you should always read the notes before you watch the videos. But we'll do a lot of examples in the videos where we talk through some of the things that you should have read. So here's our first scenario. Let's suppose that we are interested in the average amount of tuition paid per semester by undergraduate college students in the United States. And we are going to select 2,000 undergraduates from across the country and collect this information. So one of the first things you do in any study is you identify what your population is. The population is basically defined in terms of the group of interest. It's the group you want to make some statement about. That's what our population is. It's defined in terms of a desire for knowledge is the way I always think about it. We desire some knowledge about this group. That's how we define our population. So in this case, the group of interest, and do be careful here, it's all the undergraduate college students in the United States. That's the group that we want to be able to make some statement about. We are interested in undergraduate college students in the United States. So be very specific in terms of how it's laid out in the problem. You want to word this in a very similar way to what basically the group of interest is from our example. So obviously in these cases, we typically do not collect data from every undergraduate student across the U.S. There's multiple reasons for that, but that would be a very expensive process, obviously, and probably not a very reasonable process. And we'll talk about that a little bit later as well. So what we typically do instead is we take a sample. And what a sample is just a subset of that population. So we're going to take some smaller group from that population in order to collect data. So in this case, instead of collecting data from all undergrads, we're collecting data from just simply these 2,000. So the sample in this case is the 2,000 undergraduate students that we select. The data, that's pretty straightforward. That's the list of data or outcomes that you get from those 2,000 undergraduates once you take your sample. The variable. So a variable, just like in algebra, a variable is something that's going to change. It's something that in statistics, the way we think about it is it's something that's going to change from person to person. So we have all these individuals, these undergraduate students. They're all going to pay a different amount. I mean, some of them might be the same, but most of them are going to pay different amounts of tuition. So that's what a variable is. We have different outcomes for different individuals. And in statistics, that's how we define our variables. So when you collect data from some population, you could collect one variable. You could collect 50 variables. If you ask a 50-question survey, then you have 50 variables, and that can get very messy computationally when you go to analyze that data. In this class, we tend to focus on mainly 1 and 2 variables. If you take any more advanced statistics, then lots of times that's something that you begin to talk about in a second semester class is what happens when you have more than 2 variables. So the variable in this case is what we're measuring, what's going to change from individual to individual, which is that tuition paid per semester. So each student is going to have a tuition paid, and that, of course, that is our variable. That's what we're collecting from each individual. If we collected another variable like their political preference, then that would be a second variable that we could add to this study. But in this case, they're just a single variable, and it's that tuition paid per semester. A parameter. So these next two terms kind of go together. The idea of a parameter and a statistic. This is how we always set up inferential statistics, is we always set it up where we basically use a statistic to estimate a parameter. So a parameter is a value from the population that you want to know. That's really what it is. So the parameter always corresponds to the population. So that's important. It's some specific value from the population that you want to calculate or that you're interested in. So in this case, the parameter is just that average tuition. So there's a single value out there at this moment in time that would represent that average tuition paid for this population. And the parameter always goes with the population. Now keep in mind with the parameter, you're not actually going to know what the parameter is. The only way to actually have that value would be to actually collect data from everyone, and then there would be no error, and you could get a perfect value for this parameter. But there is some perfect value out there at this moment in time that represents the value for this parameter. Of course, next semester, that average tuition will change. So this is always a moving target, which it is lots of times when you're estimating things. Uh, the other term that goes along with the idea of a parameter is a statistic. So a statistic is exactly the same thing as a parameter, except for it relates to your sample. So a parameter is the average, or not the average. A parameter is a numerical characteristic of your population. A statistic is a numerical characteristic of your sample. So in this case, if the parameter is the average tuition paid for the population, then the statistic is simply the average tuition paid for the sample. And ultimately what we do is we don't know what the parameter is, so instead of calculating it, because we're not going to collect data from the whole population, we take a sample, we calculate our statistic, and we ultimately use our statistic to estimate our parameter. And of course, through this process, there is error. And it goes back to the idea of what I talked about when I talked about the president's approval rating. If the president's approval rating is 40%, that 40% is a statistic. It's a value that they calculated from their sample. And then, of course, there's error in that when you go to estimate it for the population, and that's where that interval we talked about earlier comes from. It comes from the fact that we haven't collected data from everyone. So this is pretty unrealistic and not very common, but if we had taken measurements from all undergraduate students in the U.S., we do call this a census. And a census is something that's very rare in statistics. You hardly ever see it. You will see the U.S. do a census every 10 years. Of course, even their census is not perfect. It is very good, though, for such a large population. About the only other time you'll see a census is you will sometimes see a census if someone has a really small population. If you have a population of 100 people, then maybe you'll do a census and collect data from all 100 people. But otherwise, a census is very uncommon, especially in the business world, because at the end of the day, a census is really, really expensive, and it's never going to be worth the cost from a monetary point of view. I've already mentioned this, but I do want to make sure that it's clear in terms of this example of what we're doing here. Whenever we go through this process, and we have this process of using these 2,000 undergraduate students in order to estimate students in the U.S., that falls under the branch of statistics of inferential statistics. And there's a few things that go along with inferential statistics. One is there's error. So when we're estimating, there's error. But at the end of the day, all inferential statistics it's that idea of using a sample to estimate a population. And when you go through that process, of course, that estimation process from a sample to a population, you know there's going to be error, which means that's going to fall into this category of inferential statistics. The other scenario that we mentioned, we said it's not very realistic in this case, is the scenario where what if we actually did collect data from all undergraduates in the U.S., and we just summarize that information. Then we have all of our data, and assuming we make accurate measurements, then there is no error. So that does fall into the area of descriptive statistics. So descriptive statistics is when you're just summarizing the data that you have. And there's a few ways that this can work. It can work in terms of your population, like we mentioned here, where you actually do a census and you collect data from your population and you say, for this population, these are the characteristics based on this data. It can also happen where you take a sample and you just summarize your sample. And this is one of the things that we do early in the semester, is just collect data from a sample, and then we describe our sample, and we say, for this sample, these were the characteristics that we saw. Now, notice that we're not trying to make inference about the population when we're just using descriptive statistics. However, those descriptive statistics will be important whenever we get to the idea of inferential statistics and how we estimate that population based on the sample. Another thing that's key as we begin the semester is just making sure that we're clear on the different types of data. So once you go through the study and you collect your data, the type of data that you end up with is very important. And there's really two types of data. Data is either qualitative or quantitative. Qualitative data just means non-numerical data. Quantitative data is numerical data. You do have to be a little careful with my definition of qualitative. If you're talking about a qualitative variable and I say it's non-numerical, I really mean by that there's no numerical meaning to the outcome. So it is possible sometimes, and there's an example of one of these on here, it is possible sometimes to have a number that really has no numerical meaning. If you just use a number as an identifier, then it is still a qualitative variable because it's not like you're going to perform mathematical operations on those numbers. So let's just go through some. What you got to be able to do with these, especially here at the front, is just if I give you a variable, you should be able to tell me whether it's qualitative or quantitative. If it is quantitative, there are two categories that go within that. Some qualitative variables are discrete and some are continuous. Discrete just simply means that the outcomes are countable. Continuous means that the outcomes are measured. So that's a pretty simple way to distinguish between discrete and continuous. Ultimately, discrete variables, they're things that you count, but ultimately what that means is that you have these specific points along the real number line that represents the outcomes for this variable. It's like how many kids someone has. You have 0, 1, 2, 3, 4, and so on. Notice you can't have 1.5, so it's not something that is continuously broken down, which mathematically is the difference in a continuous variable. Continuous variable is like what you study in algebra, where you have this continuous scale where between any two distinct points there's an infinite number of other points. So if you look at something like weight, well, you can have 1/2 of a pound, 1/4 of a pound, 1/8 of a pound, and you can continuously break down that scale, and that's what happens when you measure something. So let's look at a few of these. The number of hot dogs sold at a Cincinnati Reds game. So the outcomes are going to be 0, 1, 2, 3, 4, and so on. So that is definitely quantitative, but it is discrete because it is something that you count. Religious preference. So religious preference is obviously non-numerical. When you have something that is non-numerical, it's always qualitative. That's a simple one. That is always a qualitative variable when you have something that the outcomes are not numerical. Here's one you have to be a little careful of. So make sure you pay attention to this idea. Student ID number. Student ID number is obviously a number, but that number has no numerical meaning. You're not going to add two people's student ID numbers together, and if you did, it would be meaningless. There's no mathematical meaning to those outcomes, which makes that a qualitative variable. There's no numerical meaning to the outcomes. A person's weight. A person's weight is definitely something that you measure. It's quantitative, it's numerical, so it's definitely quantitative and continuous. And the way I always think about these is just think about if you can continuously break down the scale. Can you have 1/2 a pound, 1/4 of a pound, 1/8 of a pound? And if you can continuously break down that scale, then you know it's a continuous variable within that quantitative category. Number of students in a class. So once again, you're counting. So that is quantitative discrete. Temperature outside in Fahrenheit. In that case, you are also measuring. So that is a quantitative continuous variable. And once again, you can have 1/2 of a degree, 1/4 of a degree. You can continuously break down that scale. And when you can continuously break down that scale, that means it's a continuous variable. Okay, so we've talked about most of the basics. The basics are just those ideas of population, sample, parameter, statistics. These are really, really important terms. I don't necessarily make you memorize every single term that we cover in statistics. You can always look them up. But with those common terms, you just have to learn what those things are because I'm going to throw out the term statistic, parameter, sample, population. You're going to hear me say those all the time, and it's going to be hard to follow the conversation if you don't get a grasp of what those basic terms represent. So it is important, especially with these basic terms, that you get locked in on those and you understand them when you hear someone talk about them. The other component here, of course, when you start is you got to be able to classify your variables. It's very important because when we move into how we analyze data, you basically analyze discrete and continuous data in a very similar way, but mathematically You have to use different techniques because when you have specific points along the real number line, you use different methods mathematically than when you have this continuous scale. So while the idea is the same between discrete and continuous variables, the reason why we break those out is in terms of how they work with probability. We have to think about those differently. So it's really important that you get good at distinguishing between what's qualitative, what's quantitative, and within that quantitative realm, discrete and continuous, because the probability works differently depending on whether your variable is discrete or if it's continuous. Okay, so let's talk a little bit more about this idea of a sample. So the terminology that we use is we say we want our sample to be representative of the population. So what is a representative sample? Well, a representative sample is basically a sample that's going to give us a good estimate of the population. And when we say representative, let me just give you some example. Suppose that we have a population that is 50% female. If our population is 50% female, then we basically want our sample to look the same way. We want our sample to be 50% female. So if our population is 10% from Lexington, then we would like our sample to be the same, 10% from Lexington. So that's the idea of what we mean by representative. We want our sample to look like our population so that whenever we go to measure it, it's going to give us a consistent value with our population. And we know that to be true mathematically. If our sample is consistent with our population, then it tends to give us a good measure. So how do we make it representative? Well, the thing that you cannot really do is you can't just really sit down at your desk and force your sample to be representative by saying, I'm going to make sure 50% is female and 10% is from Lexington. And of course, the reason why you can't do that is because, well, how many variables are there out there that you would have to account for? And the problem is who knows? There's an uncountable number of variables. So you can never account for all of these possible variables out there that could create differences in your sample, between your sample and your population. You're never going to account for all those. So we have to use another technique in order to do this. So the way that we do this is it's based on how we take our sample. And I mentioned this earlier. How you take your sample is super, super important in terms of what you're able to do mathematically and statistically. Ultimately, what we should do is we should take a random sample, which seems kind of odd on the face. All a random sample is really just a sample that's determined by chance. So a sample that's determined by chance is really the way that we make sure that our sample is representative of our population. So at first thought, sometimes that seems a little unusual, but if you really think about it, it really does make a lot of sense. And I'm going to discuss why this works, but let's just talk about the idea of bias first. So if we take a sample that is not random, then what happens is it runs the risk of being severely biased. So bias is what we try to get rid of. And the nice thing is if you truly take a random sample, then our sample will actually be unbiased. It won't tend to overestimate or underestimate the parameter of interest. So the first thing you need to make sure that you grasp is just the idea of getting a representative sample comes from taking a random sample. And if we truly take a random sample, it eliminates bias. A representative sample will not have what we call bias. And like I said, bias is basically a prejudice in one direction. It is where you tend to either select your data set in such a way that you overestimate or underestimate the parameter of interest. And that's what happens when you start to deviate from a random sample. You start to be in this situation where you favor the selection of individuals with certain characteristics. And when you favor the selection of individuals with certain characteristics, those characteristics are probably going to impact the variable you're interested in. So what's going to happen is when you favor the selection of a certain characteristic, it's either going to pull your estimate to the right, making it too high, or to the left, making it too low. And that's what we call bias. It's when you're collecting your data in such a way that it's pulling your statistic to the right or the left of your parameter, and you're not really getting a good estimate like you want. So let's talk through this. So why is a random sample actually representative of the population? Why does this actually work? And if you really think about it, it makes a lot of sense, but you really do have to think about this to wrap your head around it. So I'm going to use this example. So this is an example that I really like to use because it's very easy to follow as we talk through this situation. So suppose we want to estimate the average income in the state of Kentucky. We take a sample of 1,000 people in order to estimate this value. So let's first just define things. So in this case, my population is the residents in the state of Kentucky, right? That's the group of interest. My sample is these 1,000 people that I'm going to collect data from. My variable is the income. The income is going to be different from individual to individual. The parameter is the average income for the state. That's what I'm estimating. That's what I'm interested in. And then my statistic is going to be the average income for these 1,000 people. Ultimately, I'm going to use this statistic, the average income for these 1,000 people, in order to estimate the parameter, which is the average income for the state of Kentucky. And through that estimation process, we know there's going to be error. So that's kind of the setup here. So let's first talk about a scenario where we only select 1,000 people from Lexington, Kentucky. Suppose we just select 1,000 people from Lexington and we use that to estimate the state as a whole. So that falls into the category definitely of we are favoring the selection of individuals with a certain characteristic. We are favoring the selection of people from Lexington. That is where bias comes from. We are not really taking a random sample. Even if we take it randomly within Lexington, we're still not getting a random sample of the state. We're favoring the selection of people from Lexington. That's where bias comes from. Well, mathematically, what that's going to mean is this. Just think about it. If you compare the income in Lexington to the income in the state of Kentucky as a whole, what you will find is the average income in Lexington is actually higher than if you look at the state of Kentucky as a whole. So if you just think about that, it only makes sense. If I only take 1,000 people from Lexington, I'm going to overestimate the average income in the state because I'm going to get a higher income because we know the income is higher in Lexington than the state as a whole. That's what bias looks like mathematically. Mathematically, bias looks like it's a prejudice in one direction where you're going to tend to either overestimate or underestimate the parameter of interest. In this case, we would overestimate the parameter of interest. It would be higher than what it should be. So that is not how you want to take your sample. You do not want to take your sample in such a way that you're favoring the selection of individuals. So the nice thing about a random sample is a random sample doesn't do that. A random sample, you're equally likely, if you take a simple random sample, which is what we'll talk about in a minute, you're equally likely to get any group of 1,000 people as my sample from the state. And that's the kind of thing that we want. We want this to be random. We want it to be determined by chance. So in order to illustrate this, let's just talk a little probability first, and we'll really get into a decent amount of probability in the class. But for now, let me just throw out some basics so that we can talk about how this works mathematically. So what I like to start with is something like, let's just suppose we flip a coin 10 times. If you flip a coin 10 times, how many times are you most likely to get tails? And of course, the answer to that is 5. You're going to get tails half the time, typically. Now, if you flip a coin 10 times, are you always going to get 5 tails? Of course not. Sometimes you're going to get 4. Sometimes you're going to get 6. You could either get 0 or 10, but those are really, really unlikely. You're most likely going to get 5, but you could get 4 or 6, or you could get 3 or 7. Those are possible. You could even get 8 or 2, and you could get 0 or 10. It's just the further you get away from that 5, which is, we know 50% of the time we're going to get tails in the long run, the further you get away from that, the less likely that outcome is. So the probability is going to tell us that we're going to be most likely to be right at that mark of 5. Let's think about what happens if I flip the coin more times, because this is another thing that comes into play in statistics. What happens is if instead of flipping the coin 10 times, I flip the coin 100 times? Well, if I flip the coin 100 times, then I'm most likely to get 50 tails. I may not get exactly 50, but what's the probability that I get 0 tails or 100 tails? And what you'll find there is that's almost never going to happen. Now, could it happen? There is some probability that you flip a coin 100 times and you get 0 tails. But that probability is so small that it's almost never going to happen. So when you move from flipping the coin 10 times to flipping the coin 100 times, you are basically reducing the probability of getting those 0 or 100, because you're way less likely to be way out there on the extremes when you flip the coin more times. You're much more likely to be close to that 50% mark. So that's the other part of probability that plays into sampling, is if I increase the number of times I flip the coin, then I'm going to be more and more likely to be close to that 50% mark. Okay, so let's talk about that in the context of this example. And I'm going to oversimplify this a little bit just so that it's consistent with the coin, and I can make a comparison here. So let's just assume that we have a population that is 50% male and 50% female. So suppose and I know this isn't true, but suppose the population in Kentucky is exactly 50% male and 50% female. Well, if I randomly select 10 people, I'm most likely to get 5 females. Now, could I get 4 or 6? Yes, I could. But I'm most likely to get 5. I'm not very likely to get 0 or 10, but it could happen. So I'm most likely to be close to that mark, that 50% mark, like the population looks. I'm most likely for it to be consistent with the population. If I want to increase the likelihood that it's consistent with the population, all I have to do is take a larger sample, because just like with the coin, if I move from 10 to 100, then whenever I move to a sample size of 100, I'm much more likely to get a sample that is 50% female, and it's more likely to be consistent with my population. And that's the way it works. The bigger sample you take, the higher the probability is going to be that you're going to be close to what you're trying to estimate. So you can always get closer by taking larger samples. So the nice thing about this in terms of representation is it a guarantee that my sample is going to be the same as my population in terms of males and females? It's not a guarantee, but the probability is really high. And the key thing is I'm not favoring the selection of any individuals, because that means whenever I ultimately go through this process, I may not get a perfect estimate, but I'm not more likely to overestimate or underestimate the parameter, which means how we define it in statistics means there's no bias in the statistic, because I'm not selecting my sample in such a way that I'm going to overestimate typically or underestimate typically the parameter of interest. So that's how we get rid of bias. If you truly take a random sample, there is no bias in your statistic, because you're not favoring the selection, which means you're not typically going to overestimate or underestimate the parameter. What if we think about geographic location? What if 10% of my population is from Lexington? Well, what will happen when you take your random sample? What will happen will be about 10% of your sample will typically be from Lexington. It works the same way as males and females would work. Now, the larger sample I take, the more likely it is to be close to that 10%. And the nice thing about random sampling is not only does it work for males and females in geographic location, but it also works for every one of those other uncountable number of other variables out there that we don't even have to think about. It works for all these external variables all at the same time, and what we know is we know the probability is going to be highest that our sample is consistent with our population in terms of all of these variables. We also know that I can increase that probability by taking a larger sample, and that's the way it always works. So there's two key takeouts here. The first one is, how do you get rid of bias? And that is, you take a random sample. A random sample eliminates bias. It gives you a representative sample. That's number one. The second thing you get with this random sampling process is you have the ability to calculate and control probability. We can calculate it because it's random, and when you do things randomly, you can calculate probability. But the big part of this is not only can I calculate, I can actually control how much error there's going to be. Because as we just said, as I increase the sample size, as I flip the coin more times, I get less error. I'm more likely to be at that 50% mark. It works the same way with sampling. As I take larger and larger samples, I'm going to reduce my error. So if you want your error to be small, then you just have to make sure you take a large enough sample to make sure that your error is small. And it's kind of like most things in life. If you want it to be better, you can make it better. You just got to take larger samples, which ultimately means you got to spend more money. It always costs more money to get less error when you do inferential statistics. That's basically the way it works. Okay, so that's the idea of a random sample. Like I said, 1, random sampling eliminates bias. 2, it allows us to calculate and control the probability of error. We control it through the sample size. Okay, so there are a bunch of different ways to take a random sample. There are a lot of them. We only talk about one of those in this class, which is the idea of a simple random sample. So what a simple random sample is, a simple random sample is a sample where all samples of, in our case, if we're using a sample size of 1,000, it's the scenario for the income in the state of Kentucky. If that's our situation and we do a simple random sample, that means every sample of size 1,000 has an equal probability of being selected. So that's the idea of a simple random sample. It's the most common type of sample that we take in statistics. It is also the easiest to deal with mathematically. So everything that we do in this class, we are just going to assume that the data comes from a simple random sample where all the probabilities are the same. I do want you to understand that there are some reasons why we might do something besides a simple random sample, and there are other techniques where you can still select the data by chance, but the chances might not just all be equal. But there are some ways to select things by chance where all the probabilities are not equal and it is still a random sample. A simple random sample specifically means all the probabilities are the same. So do distinguish between what a random sample is and what a simple random sample is. A random sample is that overall idea of all samples where you can calculate probability. If you can calculate probability because what you do is determined by chance, not necessarily equal, it could be equal or unequal, then that is the idea of a random sample. A simple random sample is one type of random sample, which specifically says that every sample has an equal chance of being selected. That is the idea of a simple random sample. And like I said, this is the most common type of sample, and it is also the easiest to deal with mathematically, and it's what we do in this class. So I think that's the basics of this first section. This first section is really an intro to the material, talk a little bit about sampling and how we collect data. This is really important information to get your head around because these are things, and that's true in this class in general, is when we cover something, we use it continually as we move throughout the semester. This material is kind of comprehensive by nature, so it's very important that you get a good grasp of this material as we move forward. But that's it for section 1.